An operational amplifier, or an op-amp, is a circuit element that looks like this. We can use this op-amp to amplify an input signal and create a stronger output signal. What we have are two inputs and an output that we'll see a little bit more detail in a moment. If you want to see a op-amp in a practical application, if you're actually building a circuit, you'll use what's called a DIP chip. A DIP stands for dual inline package, and the idea there is that you've got a line of pins on one side, a line of pins on the other, that these are all in a line, those are all in a line, and then they're in a line across the chip as well. And it's designed like that so that you can plug it into the center of a breadboard as the centerpiece of a amplifying circuit. You've got these 5 primary terminals, again the inputs and the outputs, and then a couple terminals that are needed to operate the chip. Each one of these terminals in the circuit model shows up in the actual chip. So you can kind of imagine inside this chip we have our inverting and non-inverting inputs. And so you can imagine the op-amp looks something like that, where you plug into one pin, goes into one part of the op-amp, the other pin goes to the other, the output goes out there, and then we have our V plus jumps over and comes on this side. Our V minus, again the other powering voltage, plugs into the other side there. Then we've got a couple offset nulls. Those are for secondary circuits that can account for some signal degradation if the op-amp's getting a little bit older, but to be honest, usually these chips work fine with very little degradation, and then one day they go poof and you get a new one. So usually we don't worry about these. If you have an NC, that means no connection, and there's just nothing connected to that pin, and you can just ignore it. But every sort of circuit we have is going to have a circuit diagram that compares the model we have to the actual chip that you'd be using in real life. So if you're using an op-amp, again, you've got an inverting input is the negative sign, that's this one right here, and you've got a non-inverting input, which is that one there. And so you've got a VP for V positive goes to your non-inverting input, VN or V negative goes to your inverting input. And then we have our output terminal, and we have VO for V output measured on the other side. And all 3 of these voltages are measured relative to the same reference. You could imagine that as being the ground of the system. And so in order to make this op-amp operate the way it's supposed to, you have to bias the op-amp. What that means is you have to apply voltages, a positive voltage at V plus, positive relative to the ground, the common node, and a negative voltage at the negative. So if this is 0, you're dropping voltage. This is now a negative voltage. And the voltage difference there kind of puts the innards of the op-amp in the proper state so that it can function the way that it's supposed to. If we want to model the behavior of the op-amp, we've talked about there being the 2 input terminals, VP for the non-inverting input and VN for the inverting input. What happens is the output voltage of the op-amp depends not on either one of the inputs, but on the difference between the inputs. If the difference between the inputs is between the 2 biasing voltages, the 2 source voltages, then you're in this linear region where the output voltage is proportional to the difference between those voltages, where A here is the gain of the op-amp. And then if you go too far one way, if your voltage goes too high, then you saturate, and the output voltage just becomes a constant value. Essentially, that positive source voltage goes straight out to the output, and so it's a nonlinear operation anymore. It's a constant output voltage, and then the same thing is true if your voltage difference goes too large negative, then you go into negative saturation, and your value is the negative source voltage. We've been talking about resistive networks, where we have linear circuit elements, and so if we want to tie op-amps into those sort of elements, we're interested in where we have the linear behavior. So we're interested where this difference between the input voltages multiplied by the gain of the op-amp is between the negative and positive ends of the source voltages. As long as we're between those 2 extremes, we're in the linear region. Typically, the gain of the op-amp is quite large, and typically our source voltages, or our supply voltages, are somewhere between 10 and 20 volts, And so what we can do is say that if Vp minus Vn times A has got to be less than the supply voltage, then Vp minus Vn has got to be less than the supply voltage divided by the gain. Since this is about 20 and this is maybe on the scale of 10,000 or so, this difference has to be very, very small. If we're going to deal with an ideal op-amp, and for an ideal op-amp, the gain is not just very, very large, but is in fact infinite, then to stay in that linear region that we're interested in, we have to have the two voltages being constant, or being equal to each other. And so that's going to be the model that we'll use typically, is we'll often assume that the two inputs of the op-amp are the same voltage, and then the rest of the circuit does whatever it has to do to keep these two being the same value. When we have an op-amp circuit in operation, we have the op-amp and it's got the 5 different terminals that are connected to different parts of the circuit. The input resistances are very large. The resistance here is approximately infinity for both of these because of the internal workings of that op-amp. And so if that's the case, these currents are typically 0. That's going to be another assumption that we'll make. Then the current at the output is going to come from these two voltage sources. That's why we need these sources there to pump energy in so that the output current can be whatever it needs to be so that the the input voltages can be the same, because again we assumed typically the two input voltages will be equal to one another. And so the output current is going to be whatever it needs to be to make that be the case. Typically an op-amp circuit functions with feedback. Specifically, we usually use it with negative feedback. What that means is that there's a connection from the op-amp's output to the inverting input. In that case, that is this connection right there. Because there's a direct connection between these two places, the output current can change its value to work its way backwards to the inverting input, and to change that inverting input so that these two values stay constant. And any change you make to the circuit will change the output current, that'll change the voltage at the inverting terminal, so that, again, these two terminals maintain a constant voltage. Then we want to write a KCL equation for this node right here in particular, the node here at the inverting terminal. We know that the voltages are equal to one another. That is, this terminal and that terminal have the same voltage, and we know that the currents are 0. And so you can have current flowing through all the rest of the circuit, but there's no current flowing there, there's no current flowing there, because there's a very large resistance inside that op-amp. And so we can solve that KCL equation to find VO, to find that output voltage, and then we want to check to make sure that the output voltage is going to be between the two supply voltages. So if the output voltage gets too large, then we become saturated, and the output voltage is just the positive supply voltage. If the output voltage is too large, negative, that means that we're not in the linear region, and the output voltage is just the negative supply voltage. And if the output voltage is in that range between the supply voltages, that means we are in the linear region, and all of our calculations here will give us the proper answer. You do not necessarily have to have that negative feedback loop that we were talking about. Again, that negative feedback loop was the part that connected the output to the inverting terminal. In this case, there is no direct connection between the inverting terminal and the output. There's no connection inside the op-amp, and there's no circuit connection outside. In this case, we can see that the VP, the voltage at the positive, the non-inverting terminal, is going to be 0 because we're connected directly to a ground. All of these are considered to be a common node or a common ground. And we can see that if the current here at the inverting terminal is essentially 0, then there's no voltage drop across this resistor because there's no current passing through it. So the voltage here, Vs, would be the same as Vn. And so in this case, we can say that our output voltage is the gain of the op-amp times the difference between those two voltages at the two terminals. We just said that the voltage at the non-inverting terminal was 0 because it's directly connected to ground. The voltage at the inverting terminal is essentially Vs, the source voltage, because there's very little current here. We can say there's essentially 0 voltage drop between those two. And so here we have an equation for the voltage the output voltage that depends on the gain and on the source voltage. Here we have some voltage source. But again, remember that the output voltage is limited by the output voltage has to be less than that supply voltage from the biasing supply sources that we have there. And this output voltage we just said was A times the signal voltage. And so if this is still the case, then we can say that the Vs, this source voltage, has to be less than the supply voltage divided by the gain. And we said that this is usually 10 or 20. This is usually on the scale of about 100,000. And so this voltage here, the voltage from our signal, has to be very tiny in order for this to not be saturated. And so what that means is that usually it is saturated. And that means that the output is usually just VCC or negative VCC, depending on whether this is slightly greater than 0 or slightly less than 0, because it would have to be almost perfectly 0 to be in the linear region.